Section 14.6, triple integrations. So in this section we will see triple integrals, and then we will use that to find volumes of solid regions. So this example here is not about a volume. We'll see on the next page how we find volumes of solid regions, but this is just a practice of a triple integral. Pay attention to the fact that when you have an integral, the limits of the integral can always include variables that will be integrated later. So in the most inside integral, it's an integral in terms of z. It is okay to have x and y in the boundaries of the integral. And then in the second step, we are integrating in terms of y. It is still okay to have x. And then in the last integral, you shouldn't have any of the variables anymore. The process is very, very natural when we integrate. We did it with one integral, two integrals. It's just the same with 3, 4, 5 integrals. You just go from the inside out. So this integral sign corresponds to dz, and then the next one corresponds to dy, and the last one corresponds to dx. Integrating is not that difficult. So in this example, we first integrate in terms of z. So maybe we want to distribute e to the xy, e to the x times y plus 2z e to the x, and this is what we get when we integrate. Now we can substitute, and here you see that we have an integrand that is only in terms of x and y, so that's perfect. We can distribute and put like terms together, and once we are in a cleaned up situation, we can now integrate in terms of y, and again, this is not very difficult. So we eventually reach the place that is represented here. Now, e to the x times x cubed. If we want to integrate that, we need to use integral by parts. That's something we can do, but notice that it's going to require quite a few steps, because when we take the derivative of x cubed, it's going to be 3x squared, so we will still have an integral of e to the x times 3x squared, and we'll have to do it again and do it again, and maybe a fourth time. So this is where we might want to use tabular integration. What you do is you write two columns. One has u and its derivatives, so u is here x cubed, and you want this one to vanish to 0 when you differentiate many times, and the other one will represent v prime and its integrals. So you want to pick something that is easy to integrate, and here e to the x is obviously an ideal choice. So x cubed differentiated is 3x squared, differentiated 6x, 6 and 0, and then v prime is e to the x, so it remains e to the x the whole time. And therefore, the integral of e to the x times x cubed is, you go like a shoelace in diagonal, and you have to alternate the sign. So x cubed times e to the x minus 3x squared times e to the x plus 6x times e to the x minus 6 times e to the x. If you're wondering why there's pluses and minuses, then just doing two steps of integral by parts will show you. It's the minus in front of the integral that is just causes this flip to happen. So we have the integral here, x cubed e to the x minus 3x squared e to the x plus 6x e to the x minus 6 e to the x, and we just substitute 2 and 0 to get the final answer. So in one dimension, to find the length of a line segment, you can just integrate from a to b, and it's going to give you b minus a, quite obviously. In 2 dimensions, the area of a region can be found like this, and in 3 dimensions, the volume is going to be just the same, but with one more integral. And here again, it shows what we discussed earlier. The most inner integral can have the other two variables, and then the middle integral can have the outer variable, and finally you need two constant, or at least no variables that have been integrated already. So the difficult part is to be able to figure out these boundaries of our integral. So if you are given a solid region like this one here, you want to decide the order in which you're going to integrate. And to do that, notice that the most outward integral has two constants. So you want to be able to pick one that doesn't depend on the other variables. So here, if we chose x as the outermost integral, it would not be the right choice, because x, it depends. Here x goes from 1 or from 0 to 2, and here x goes from 1 to 3, so x depends on y. Z also depends on the other variables. Here it goes from 0 to 1, but at the end it goes from 0 to 0. So the only possible choice in this case is to choose y as the outermost integral, because for every point, or whatever we choose for x and z, y is going to go from 0 to 1. So y goes from 0 to 1. And now that we've fixed the interval for y, we can look at x. If I choose a random value of x here, if I choose a random value for y, I should have said, then x ranges from here to there. So I need to find the equations of these two lines, and they are given. So x ranges from 1 minus y to 3 minus y. And finally, for a fixed value of x and y, let's choose this point in the xy plane. What does z range from? Z goes from 0 to the roof here of this shape, which is 1 minus y squared. So this is why z goes from 0 to 1 minus y squared. Notice that this could also have some x's in it. In this particular example it doesn't, but it could. So we found the limits of our integrals. Z goes from 0 to 1 minus y squared, x goes from 1 minus y to 3 minus y, and y goes from 0 to 1. In this exercise, we're going to practice switching the order of integration. So here for this example we have dz, dy, dx, and we want to change this integral to the order dx, dy, dz. The integrand itself doesn't change. What we will have to pay attention to is what happens to the x, y, and z ranges. So just like when we did it for double integrals, it's very important to sketch the region of integration. In double integrals it wasn't too hard because it was in the xy plane. Here the region of integration is actually a solid in space. So x ranges from 0 to 2. So that means x ranges from 0 to 2. Then y ranges from y equals 0 to y equals 2 minus x. So for a certain value of x that I picked, y ranges from 0 to 2 minus x. And then, so that creates this triangle in the xy plane. Finally, z ranges from 0 to z equals y squared. So there's kind of a parabolic top here. If I choose a certain point, let's pick this one here, then I will go up until I hit this curved that is at z equals y squared. So it gives this kind of complicated, very pointy shape in 3 dimensions. And that's the key intermediate step if we now want to deconstruct this solid and redetermine the ranges. So now z is the outermost integral, so it is not allowed to have any other variables in its range, and indeed z ranges from 0 to 4. That is very clear. For a certain value of z that we would pick, let's say take this one, y ranges from here to here, which is from square root of z, from y equals square root of z, to y equals 2. And finally, x ranges for each of these x ranges. If I pick a certain value yz, I would be moving until here somewhere, and that would be from 0 to 2 minus y. I would be hitting this wall that is vertical from y equals 2 minus x. So that's how you integrate. Notice that this does not define a volume. If we wanted to find a volume of this shape here, we would have the same setting for the boundaries of the integral, but it would be of 1 times dz dy dx. So how can we interpret this integral? There's maybe 2 ways to think about it. The first one is to think we are finding a hypervolume in 4 dimensions. And the other one is that we are actually looking for the mass of this object where the density function is given here. So the density would vary depending on x, y, and z. It would be very dense in some places and not dense in others. So what would be the mass of this object? So if we want to find a volume, as I said, it's the triple integral of 1 times dz dx dy. So the key is to be able to define the boundaries of my integration. So for this shape, 4x squared plus 4y squared plus z squared equals 16, we can make our life a little bit easier maybe by only focusing on 1/8 of this volume and multiplying by 8. And that'll allow us to always integrate from 0 to something. So I think that's pretty much every option is possible for the order of integration. Here the order chosen was dz dx dy. So first let's look at y. Y goes from 0 to 2. And then if I choose a certain value of y, then x goes from 0 to 4 minus y squared. So how did I find that? I set up z equals 0 because we are in the plane, and I solve for x. And finally, for a certain value of x and y, how high do we go? It's approximately, so here would be where we hit the ellipsoid. Then you solve for y, so you solve for z, sorry. So z equals square root of 16 minus 4x squared minus 4y squared. And you can do it with your calculator, or maybe sometimes we can do it by hand. This time maybe not. Anyways, the volume of this egg is 67.021. Thank you for your attention.